Okay, what we're going to try to do here is just set up to do spherical integrals. We're not going to actually do any yet. Just a reminder about how we actually had to set up earlier integrals. When we did double integrals in rectangular coordinates, we had to have a function involving those coordinates, and then we also had to have dx dy, and that actually meant something. Remember, these came from delta x, delta y, and that was actually a little area, and that we were actually multiplying something times a little area, and that was very physical. When we did polar, we had to have f of r theta, and then I had to have an r dr d theta. And remember, this came from our delta theta, and that also was a little tiny area. I remember how we got that, by the way. How did you get this one, right? We drew x as constant, then made a slightly bigger constant. We drew y equals a constant, then a slightly bigger constant, and then we looked at the intersection, and it was a little tiny rectangle. We did the same thing here. We drew theta as a constant, then theta slightly bigger constant, and then r as a constant, and then r a slightly bigger constant, and we got the same thing, and so we actually got an area. This is the hard part about setting up the integrals. When we did triple, right, when we had some sort of solid, right, usually you have some sort of function of 3 variables, and there we had something like dx, dy, dz. And by the way, remember here, we could also call that dA. We could also call that dA. This one here, they'll usually call dV if they call it anything, right? But remember, this came from delta x, delta y, delta z, and we made that little box here the same way we made these little boxes. But this corresponded to having a little volume. If we're going to do an integral in spherical coordinates, we're going to have a little spherical box, whatever that means, and be able to calculate the volume of that box. And that's what's going to actually be in every spherical integral that we do. Now, we're going to unfortunately have to try to draw this. I'll try to get you a really good picture. I just want to draw well enough so that we can see what the picture comes from, and then we'll look at a good picture afterwards. So what am I going to do? We're going to be in 3 space. What I want to do is pick a point, and what we're going to do is draw r as a constant. Okay, I think that's good. Now what I want to do is draw r as a slightly bigger constant. Well, that's just going to go up like that. If I draw a phi, remember phi comes down this way, and I'm going to erase that because I'll probably need it. A slightly bigger phi would come all the way down to here like this. And what we want to do is draw the intersection of like that. So that's going to come like this, that's how it's measured, and that's going to come down like this, and that's how that's measured. Now the hard part is changing theta, because theta is measured way down here, and making theta a little bit bigger means the shadow down here would have to be a little bit of curve. So what I want to do is draw something up here whose shadow is down there and it looks like that. So I'm going to draw something that looks like that, and we have to do that at all the corners. So that's going to look like that, and then look like that, and then this is going to come down like this, and then the radius comes down like this, and then this is going to be the change in phi as I go like that, and this is going to go like that, and whoa, you see what I'm going to call a spherical box, which is a very strange title if you think about it, but we want the area, we want the volume of such a thing. Now, this has the same kind of qualities that the polar one does, is that if delta r and delta phi and delta theta are all really small, then all these angles are very, very almost perpendicular. So what we're going to say is this is almost exactly, how about we say almost exactly? There we go. Length times width times height. The height is actually just delta rho. It's just a change in the distance. That one was just wonderful. Yay. See, this distance right here is the same as this distance right here, and we know what that is, right? That was r delta theta from polar. Now what we want now is this one, and we're going to use the same kind of argument that we did when we did polar. If this was actually the unit sphere, that distance would be exactly equal to delta phi. No, it'd be delta phi. This would be delta phi. But we want this distance, and since it's not the unit sphere, it's longer, this distance is going to be rho times longer than this distance. That's just actually the arc length formula. So this is just going to look like rho and then delta phi like this. And let's put some stuff out front. So I'm going to get rho times r times delta phi times, times delta rho times delta phi times delta theta. Now, one thing I think it's fair to complain about is r. r is not spherical, but we do know from the previous video that r is actually rho sine phi. So what we're going to get here is rho times rho sine phi times delta rho times delta phi times delta theta, and I can at least multiply the two rho's together. So I'm going to get rho squared, and then sine phi, and then delta rho, and then delta phi, and then delta theta. And this is what has to show up in every spherical integral that we do. In the same way that r d theta has to show up in every polar, rho squared sine phi, and then d rho d phi d theta has to show up in every spherical. And this is why I will post the usual picture that people put in. It's a better picture, but at least you can see how we got each of the dimensions and how we calculated the volume.